Good morning everyone, and welcome to today's worked exam answer video. Today, because I am a little bit bunged up, I've chosen a bit of a shorter question to try and save myself. And I'm going to have a look at this OCR question, which comes from one of the AS papers, but of course is something that is applicable for those of you not only in year 12 but also in year 13. For any AQA students watching this, you would need to be familiar with the top left box and the two at the bottom, but less so with this one. However, I still think it's quite a good thing to be aware of, and I suppose it does come up when we think about benzene in terms of enthalpy of hydrogenation. So yeah, AQA students should be able to take something from this, but it is an OCR question. And it's an organic question focusing on alkenes, and we have to complete the flowchart for the reactions of butanene in the middle by adding the structures of the organic products in each box. So we're reacting with bromine, we're reacting with hydrogen in the presence of nickel, and we're reacting with steam in the presence of H+ ions. So I guess if you get a question like this, it's trying to work out or be able to retrieve from your memory the reactions that are being signposted with the reagents on the arrows. So what we're going to need to be able to do is see that we're using bromine and make that connection when we have a double bond to electrophilic addition. And so we're going to open up the double bond in the butanene, and to each carbon we are going to add a bromine atom. Now, the butanene is an asymmetrical alkene because the double bond is not between the middle two carbons, and this is why we're going to get a mixture of products down here. But I mention it now because it doesn't matter that this is asymmetrical, because the electrophile, the bromine, is nonpolar, and it's made up of the same two atoms, and therefore which carbon gets the first bromine and which carbon then gets the second bromine from that molecule doesn't matter. So there can only be one product, and that product will be as follows. So carbon-carbon double bond opens up to give us a carbon-carbon single bond, and then these two carbons are obviously not going to be changed at all. The first carbon has two hydrogens on it, and then it's going to take one of the bromines from the electrophile. The second carbon has a hydrogen on it. It then has the CH2CH3, which I've just opted to sort of draw this in a straight line as displayed formula. And then the second carbon will also take a bromine. And of course it doesn't matter if I draw the bromine on the second carbon up or down, and I draw this bromine on the first carbon in any of those three positions, because it is all the exact same thing. Now, being able to outline that as a mechanism is also important, and I know it's not asked for in this question, but that might be something when you are revising and doing questions that you also just want to make sure that you're happy with. There's always more that can be done with these questions, so you could also potentially, if you wanted to, have a go at naming the products of these reactions. So this would be 1,2-dibromobutane, for example. Just some ideas, because obviously the more we know these reactions off by heart, the more comfortable we are with the mechanisms and naming, the easier the questions will be, of course. Second reaction involving hydrogen and nickel is we're going to be opening up the carbon-carbon double bond and turning it into an alkane. So we're going to make butane. The hydrogen gas is the reagent, the nickel is the catalyst for this reaction, and it's going to provide the surface on which this reaction is going to take place. And yeah, because again it's hydrogen and the hydrogen is nonpolar, made up of the same atoms, it isn't going to matter which hydrogen goes on which carbon, because the outcome is going to be exactly the same. We're just going to make butane. In terms of mechanism wise, you could do it as electrophilic addition. As a process, the gain of hydrogen can be classed as reduction, but also when we are opening up double bonds and turning them into single bonds using hydrogen, we can also call it hydrogenation. So I guess different words for essentially the same outcome. But again, it's not just knowing the names of mechanisms, it is also knowing the names of processes as well. And now I can draw in my butane. So again, if we open up the double bond, I'm going to have 4 carbons. Nothing about these N2 has changed. And then the first and second carbons have now just got extra hydrogens on. So literally just butane. And then finally, excuse me, if we think about the reaction at the bottom, we've got water in the form of steam, and we've got H+ ions. Now the H+ ions will come from some sort of acid. I think they've been a bit general here and said H+ because it could be phosphoric acid. That's the one I know it as, but I think sulfuric acid is also accepted here. And this again would be our catalyst in this reaction. So I'll put in brackets H3PO4, which is phosphoric acid, and then H2SO4, which is sulfuric acid. If we are adding water across a double bond, the process, again, rather than the mechanism name, but the process is going to be hydration. When we add water, we hydrate. If we were to remove water, we would dehydrate. And the reason we're going to get 2 products here is because of the fact that this is an asymmetrical alkene, and because the H2O, when that gets added across the double bond, one carbon will gain a H and the other will gain an OH. So the mixture of products we're going to make will be alcohols. And because it's an asymmetrical alkene, whether the first carbon gets the H and the second carbon gets the OH, or vice versa, is going to give us different alcohols. Hence why there's 2 boxes here. So in one of the boxes, well, what you might choose to do first is just have your chain of 4 carbons, which has been sort of my starting point for each of these. And then these 2 carbons are not going to change at all because that's not where the double bond is. So they will all still be hydrogens as per the butanene. And then in one of these, we are going to have the hydrogen being added to the first carbon and the OH going on to the second carbon, like that. That's one possibility, and that would be butan-2-ol. The other possibility is that the hydrogen goes on to the second carbon, and the alcohol group is therefore positioned on the first carbon to give us butan-1-ol. And they are different. They're named differently. They would class as position isomers, so a type of structural isomerism. And if we then think about what we can do with these different alcohols, they would be oxidized to give us very different things. So butan-2-ol could be oxidized to a ketone, whereas butan-1-ol could be oxidized to an aldehyde or a carboxylic acid. So that is another clue that these are different things, naming them differently, and the fact that their reactions are different when they undergo oxidation. So hopefully we can see how that's possible from but-1-ene. If it was but-2-ene and the alcohol group went either on the second or the third carbon, they wouldn't be different because you would count from left to right if the alcohol group went on the second carbon to give butan 2-ol, and then if you put it on the third carbon, you wouldn't call it the third carbon because you'd count from the right. So with a symmetrical alkene, you don't get this mixture of products in this reaction. But with an asymmetrical alkene, we do. And hopefully you can see that, and hopefully all of those reactions make sense. As always, guys, any questions, please just let me know. And thank you as always for watching. I'll catch you soon. Take care.